Hi, and welcome to the second video from the two on parametric equations, and in this video we're going to be looking at how they might examine parametric equations and put it into the context of modelling, so giving some context to the kind of question that they're going to ask. It's worth mentioning at this point in time there's a whole load of other stuff they can do with this in terms of differentiation and integration, but I'm going to deal with those when I deal with those two topics rather than putting them in with these now, because there's a whole world of other stuff that we need to know about before we can get to how we go about finding gradients and areas under these curves. Having said that, there is a little bit of differentiating involved in one of the questions I've put in this video, but hopefully it should be fairly self-explanatory and straightforward. Right, so off we go. First thing I'm going to do is a question that essentially is to do with projectiles, which is ripped from the mechanics section of the course, but again it can pop up within the pure section, but they will do it in a way such that you don't need any specific mechanic knowledge to be able to access the question. So what we've got is we've got a boy on a 10-metre cliff throwing a stone into the sea. At time t, that's going to be our parameter. The horizontal distance of the stone from the base of the cliff, so basically how far out to sea it's gone, is given by this equation here, x equals 8 root 3t. And the vertical distance from the base of the cliff, i.e. how far in the air it is, well, kind of in that direction, is given by this one, y equals 10 plus 8t minus 9t squared. So, first thing we're going to do is, it says, find the distance the stone is from the buoy when it hits the sea. So, what we've got here is when it hits the sea, we've got y value is going to be 0 because we're dealing with our definition from the base of the cliff. So we've got y equals 0, and so if we put that into there, that's going to allow us to come up with the value for the parameter t. So let's do a bit of equation solving, and there we go. Two possible answers, but clearly in this context we can't have that one because time can't be negative, so we know we've got a value of t is 2.46 when the stone hits the sea. And what that means, if we want the distance the stone is from the buoy, we need the horizontal distance as well. So that's the one we're looking for. So let's put t equals 2.46 into that horizontal equation. And so the stone has travelled 34.1 metres in that direction. We already knew that it was 10 metres below the buoy, so we want the distance the stone is from the buoy. So hopefully now we can see a little bit of Pythagoras should sort that out for us. So there we go. The stone is 35.5 metres from the buoy when it enters the sea. Okay, on we go to part B. It says find the maximum height reached by the stone. So we want this maximum height here. So what we've got for our equation in terms of vertical height is a parabola, a quadratic. And clearly the maximum height is going to be this top point here. And we know at that point it's when dy dt equals 0. So all we've got to do now is do some differentiating, come up with our value of t, so t is 40 over 49, and then so we know that the maximal height will be reached less than a second after the buoy's released it, and so when t has that value, the vertical height is simply going to be what we get when we plug in the value, and so we've got our maximum height reached above the sea is 13.3 metres. So that one was just a kind of example, was just a simple, straightforward, can we find some values for t and plug them into the relevant equations, and just understanding a little bit about the context. Finally, with a lot of modelling questions, you're going to get these kind of things, which ask you to discuss why you think it might not be the most reliable model in the world, and possible answers we can come up with here might be to do with, for example, the model doesn't take into account the height of the buoy, so we're talking about a 10-metre cliff. But this buoy, how tall is the buoy? Is he throwing the stone from above his head? Is he throwing it from, is it an underarm throw, shoulder level, whatever? We've not got no information about that. The sea is not flat yet, so clearly when the stone enters the sea, it might hit the top of the wave, which might be sizable, so that might introduce an element of uncertainty and unreliability into it. We've got the height of the cliff. We're saying a 10-metre high cliff, but at different times of the day, if we've got a tide rising and falling, how do we know the height above sea level? And in this modelling assumption that actually comes from mechanics, which is the horizontal speed of the stone is constant, but it might be, depending on the size of the stone, we might get things like air resistance and those kind of things going on, so that is an assumption that we've made as well. So you might want to just pick anything there. I would pick particularly like any of these three, as long as you say something that's vaguely intelligent in the context in which the question is set, then you're pretty much going to get the mark. There we go. Right, so that's the first example done. Second one, This is a personal favourite of mine. I am that kind of a maths geek where I can, go to Alton Towers or any other fairgrounds and I set these things and the wife's there and I'm start talking about trig equations and she starts telling me how dull I am. But what we can do is model the motion of this car using a parametric. So essentially saying how far is each individual car on this ride away from the centre of the ride. And what we've got essentially is a wheel spinning within a wheel. So you've got a small rotation, which is kind of on the end of the this central axis here, added to a larger rotation coming from the centre of the ride. So what you get is motion looking like this. And the thing with these rides, you'll feel you'll come round and then you'll be kind of flung, and it's this section here where you get almost like an acceleration of your car to the ride and get flung out to the furthest reach of the ride before you come back through it again. So that's what's going on. Like I say, my wife thinks I'm a geek, and she's probably not wrong when I start talking about trig when I'm at fairground, but hey ho. Right, let's have a look at what's going on and what the question is we're going to be asked. So there we go, there's our question. The owners want to build a safety barrier around the ride that's a minimum of 1 metre from the rotating cars at any given point. So what are the dimensions of the enclosure? Well, first of all, let's just have a little think about the curve, and one obvious thing to notice is that the curve is symmetrical about the axes, which is going to make our job a little bit easier. The other thing we've got is the maximum horizontal and vertical distances. Well, the maximum horizontal distances, if we think about because t is an angle, so this point here, our value of t is going to be 0, and this value over here is going to be when t equals pi, because obviously we're dealing with our angle in terms of radians. So we've got those 2 points there that are our maximum horizontal distances, and our maximum vertical distances, a bit less easy to find. Well, our maximum vertical distances are going to be points here, and we know, and down here as well, and we know at those points that's when dy dt is going to be 0. So when the curve is flat, as it stops going up and starts coming back down again. And we're saying dy dt is equal to 0 because we're talking about the vertical distance, so the change in y compared to t, rather than the change in x compared to t. So that's dy dt equals 0. It's also worth mentioning that we looked at these 2 points here and said, okay, we know the values of t. Also, if we've got vertical lines there, if we drew that one in there, that would be the line dx dt equals 0. So if we didn't know these values, we could find them by using dx dt equals to 0. But in this part 1, it was fairly obvious. So we're looking at those 2 points, when t equals 0, t equals pi, and points when dy dt equals 0. So that's what we're interested in. So let's have a look at how we're going to go about finding those things. So first one we're going to do is our horizontal distances. They're reasonably straightforward. So when t equals 0, what we've got is x equals 3.5 cos 0 plus 2.5 cos 0. All nice and simple. So that's going to be a maximum distance of 6. And similarly, when we put the value of t equals pi into there, that's going to give us minus 6, which we're anticipating. And so if we find when now dy dt equals 0 is to give us our vertical distances, let's go up here, differentiate. So we know if we differentiate sine, we're going to get cos, and we've got to think about how we differentiate that bit there as well. So the 3's coming out of there. So what we get is dy dt equals 3.5 cos t plus 7.5 cos 3t. Right. Now we've got to set that equal to 0. There we go. And so we've got to be able to solve that equation. Now to be able to do that, we've got to get the whole thing in terms of just cos t. We've got 2 different angles here. So we've got to take this cos 3t and write it in terms of cos t. So what I'm going to do is just jump out here for a second and go through that. So cos 3t, now it might be that in the exam you get this kind of a question asking you to prove one of these results. The double angle formula are given, but we can get higher order powers, higher order multiples in terms of just the single one. So what we're going to do is take cos 3t and write it as cos 2t plus t, and now use my double angle formula. So that's quite a nice and sneaky little trick to be aware of. So using our addition formula, there we go, cos 2t plus t equals cos 2t cos t minus sin 2t sin t. Now we've got to replace the cos 2t and the sin 2t, so let's do that with our double angle formula. So we'll use cos 2t, and I'm going to use this version of it just because I want the whole thing in terms of cos. So there we go, substitute those in. Now, that one's just in terms of cos. Now that one's okay. This one here, we've still got some sines floating around. So let's just multiply out and see what we're going to do with those. There we go. That's in terms of just cos t, cos t. Here we're now going to replace the sine squared, and we can do that using a 1 minus cos squared. Tidy up the brackets, and then just bring our bits together. So you'll notice now I've got some cos cubes, and I've just got some cos's. So the whole thing turns out to be just 4 cos cubed t minus 3 cos t. So now what we've done is taken that cos 3t and expressed it just in terms of cos t. Right, now we've done all that work, let's go back to our original question, which was we've now got to solve this equation here. And now that we know how to express cos 3t in terms of cos t, which was using that one, let's just plug that in, multiply out, and do a bit of tidying up. So this 30 cos cubed comes from the 7.5 times 4 of them there, included with, that's that one. And then the 7.5 times 3 included with those ones there. Hopefully you can see how that's all going to fit together. Now we've got to solve that. So factorise. So we're taking out a factor of cos t, which gives us cos t equals 0. Now those ones, when cos t equals 0, that gives us a value of t equals pi over 2 and 3 pi over 2. You'll notice that gives us these 2 points here, where again we've got dy dt, if you can see my cursor. So that's horizontal, so dy dt equals 0 at those 2 points. But we're not particularly interested in those, because we're interested in the ones on the outside of this path. And that's going to come from there. So let's move the 19 over, divide by 30, do some square rooting, and then inverse the cos. Hopefully you're all comfortable with that. And so we've got 4 values, plus or minus 0.65, plus or minus 2.49. So the plus 0.65, that's going to be that one there. The plus 2.49, that's going to be between pi over 2 and pi, so that's going to be that one there. And then the negative versions, we've got the minus 2.49 there, and the minus 0.65 is going to be there. So those are 4 points. So let's take our value of t. We don't need to do all 4, they're going to be the same. So let's take just the 0.650, put that into our equation for y, and there we go. There's our distance. So now, final bit we've got to do is tidy the whole thing up and think about this issue of this 1 metre gap that we need between the barrier and the cars, and think about the question asked for the dimensions of the enclosure. So we've got our centre at 0 there, so that's our point here. So we've got that distance horizontally, it's clearly going to be 7 metres, giving us a total of 14. And we've got that distance vertically, which is going to be 5.4 metres, giving us a vertical distance of, 10.88. So there we go. There's the dimensions of our enclosure. Now, there's a whole world of other stuff in there with the whole cos 3t bit. There's a little bit of differentiating there as well. Hopefully it all made sense. And let's say kind of later on in the course, you'll see more about differentiating and particularly integrating these things. But for now, that will do us for the work we're going to do on the modelling.